Hello everyone from Edinburgh and welcome to the last talk of the school where we are going to keep talking about challenges and solutions when it comes to bringing your models to production, when it comes to go from the simple workflows that you can see in academic papers and in tutorials to real life solutions for your customers. Talking about academic workflows, this is an illustration of the typical one in an ideal world. You start with just your data, maybe it's supervised, and you have an objective, maybe it's unsupervised, and you are looking to discover a structure there. You select your features, you put them together into a data set that's machine learning ready. Bring that data to a predetermined, pre-implemented machine learning algorithm. We have all of them implemented, all the important ones, in a scalable way in platforms such as BigML, so you can use your data directly to create those models, and then you end up with a set of models that can then be put to use either to understand better your input data, new input data, or to make predictions. And that's the theory, and that's something that we've solved with in the latest years with machine learning as a service and one-click solutions. Right? We know how to do these workflows and how to do them efficiently and very easily. But in your projects, you've already seen many examples these days. But let me go to the basics. Even when you start teaching machine learning, you start talking about workflows. You almost never ever do a single one-click modeling. For instance, you start explaining people, oh, don't do that, don't do a single one-click model and then go to production with it, right? Don't even use it yet. First, split your data set and have a training and a test half, and then use the training part to create the model, and then the other part that hasn't seen the training data to evaluate that. And that's already a workflow. See, yeah, it's not just an API call. It's not a single instruction. Even in our abstract world, where these resources live, where I don't need to know anything about the details of the algorithms, even there, this workflow is not an atomic operation. It has passed. I have to go over the UI if I want to do it using the UI, and click here, create a data set, then split it, then create the model, then create the evaluation. I have to do a series of steps for doing that. And of course, what happens is if I want to repeat the whole thing, what happens when I go to production, I want to regenerate these models maybe. I want to regenerate these evaluations with new data. I want to to redo or perform again my workflow. It's true that the web UI has nice properties, especially when it comes to abstract us from the details, from the algorithms, from the parallelization of all the operations. I can forget about that. I only see machine learning entities. I only see data sets. I only see evaluations, confusion matrices. All I see are things, or most of all I see are things that have to do only with machine learning concepts, and it's a simple interface, and it's easy to discover new things you can explore. So it's great for exploring your data. It's great to come up with new solutions and to get an idea of what should be done. The interactivity is a big boon, but when it comes to go to production, all the advantages stop there. It's only simple for tasks that are simple. The moment you start complicating a little bit the workflow, there are lots of clicks to do there, and it's easy to forget things, and it's difficult to keep track of all that you did. And stops easily being simple, right? And of course, there's no automation there. There's no way of, at least at this first level. Then we have Scriptify, which you've already seen, and there you can automate things to a point using just the UI. But at this stage, when all you have is a point and click interface, it's clearly difficult or not convenient to automate and repeat over and over the same thing. So what we do when we want to repeat things, what we do when we want to automate, usually as programmers, is write a script. Is we choose a programming language, and a programming language is designed precisely for doing those tasks for us, for repeating over and over things, and especially if they are boring, right? You just code them once, and you can, in theory, repeat them at will. And one nice thing maybe about this is that our APIs are very simple in terms of implementation. They work on top of HTTP. All languages in the world these days now know how to access the network arc in your computer and talk HTTP. So we have bindings for all conceivable languages, and it's very easy to write new ones. So you can just fire your editor if you have to implement this workflow again, this evaluation workflow. For instance, you just fire your editor and, for instance, write a snippet or a bit of Python code. And this can be streamlined a lot, and with good bindings like these ones, you can almost read what you are doing, the steps that you are performing, even without knowing the language. Here you see that I'm creating a data set, and then after creating the data set, I'm creating a train and a test data set. I'm splitting the original data set. You see that I'm creating a model, and you can read there, create evaluation. I'm creating an evaluation using the model and the test data set. There's already some complications, some things that are in the program that are not part of my workflow, actually. There's this API.OK calls that you see interspersed here quite often, and they are there because we are creating resources that have to be finished before we use them to create new resources. And so here we start seeing a complication. We have to remember when to stop, when to wait until we perform the next step. We have to remember that if I'm creating a data set from a source, when I want later to split it into halves, I need first to wait for it. So I need this call to API.OK. And then afterwards, I want to create a model from a training data set. I have to remember that I have to wait for it, and so on and so forth. Same thing for the evaluation. So we see here that there's already a bit of complication, a bit of noise in the definition of the workflow using Python or any other language for that matter. But even with that, this is kind of readable. It's not that bad. Am I happy with this? Should we go to production with this code? Well, let's think a bit about that. Is that enough? Another thing that we should think about when we are thinking if we want that code in production is whether this is going to scale well. Once my company is successful, instead of one data set and I want to perform this operation with 100 data sets. Can I do that easily? Can I move from the simplest case to something that parallelizes well, that scales well with the number of inputs and with the size of my data? Well, you could say, okay, this is Python, and if I have this operation for creating one evaluation for one instance of my workflow, and I want to do it 100 times, I just put here a for loop and do it 100 times serially. But why? I mean, if I'm creating, is that the really? It's simple, of course, but is that the best way of doing things? Why should I be see this calls to API OK, they are waiting. Every time I have to do the next step, I'm waiting. So if one workflow takes, say, 4 or 5 steps here, if I want to do it 100 times, I have to wait for resources like 500 times. Does that make sense in a world where we have parallel computers? Of course not. If the data sets are independent, my models are going to be independent, my evaluations are going to be independent of each other, and I don't have all the time in the world for waiting for 100 or 1,000 times this workflow to finish one after the other. So what I will want to do is to parallelize. But then I start having choices, having to deal with choices. How do I parallelize my things? There are many operations and many points, or at least several points in my simple workflow where I could parallelize things. I could start waiting first create all the data sets, and then wait until they are all done, and then go to the other tasks there. Or maybe why wait? I mean, why don't I start directly creating the model instead of waiting until all the data sets are done? Or why don't we go on and also start creating the evaluation? Well, you could think, okay, let's do that. Let's put all the things in parallel. But then there are other problems that I have to address, like how many of these processes in parallel can I launch at once? Should I start worrying about how many, I don't know how many Python processes my little computer can deal with? Because remember, I'm now on the client side. So things about the scalability, about how many cores I have, about how many parallel tasks can I run in my service are relevant again. It's not, nobody is controlling that for me. I have to control that. Even more than that, to that they have to control errors. Every step in this workflow, or many steps in this workflow, could fail. What happens if in the middle of the 25th data set or the 100th workflow instance, things fail? Should I stop? And if I stop, should I delete previous results? How do we notify other threads that are running other instances of the same workflow? How do I fix those things? It's not impossible, but it starts to be complicated. And this was a very, very simple workflow. What's going on here? Well, what's going on here is that there was a very nice abstract world provided to me by this API, by these REST resources when I create a model, even when I create an optimal, something that underneath is creating thousands of models or thousands of trees, for instance, with an ensemble. All these operations are for me at the resource level atomic operations. I ask for an ensemble and I wait. And things will go on in the server, and parallel threads spawn, and many machines put into work to create all those thousands of trees that I need for my ensemble. But I don't have to worry about that. Some of those processes will fail, and the server will retry and will make things right for me. I just wait. I want to create an ensemble, I wait, I get a result. I want to create an optimal. It's even more complicated, but I wait, I get a result. I don't have to go there and explain the machine, the service, what to do. Whereas suddenly I move to a very simple workflow on my side, and I have lost many of those abstractions that I had. I have to worry again about complexity. I have to worry again about scalability. I will worry also about reuse. When I have an API and it's all like a request and then I get my model back, I can do that with any language. I'm not obliging anyone to use any language in particular. But now if I start writing my workflows in, say, Python, I'm leaving aside the Node.js crowd. Or if I'm using C++, maybe the Java programmers or the Java applications won't be able to use that. So we are also losing reusability. And of course, the moment you start having to develop and maintain your local scripts, and to run them in environments that are on the client side, you are going to have issues about reproducibility, about being able to be auditable. There are many applications that need some control where you have to be able to reproduce exactly all these steps that brought you from the input data to a model. Think of banking or healthcare. There are regulations and there are tests that you will have to pass with auditors to be able to put your models in production. Even for you, even if you are not a bank, you want to be able to reproduce your system, your models, what is giving you answers today. You want to be able to know where it came from. You don't want your data scientist to go to Google to work there and then leave you with a bunch of code that you don't understand. So with all these problems were solved when all we wanted was to create single resources. And now that we want to do a simple workflow, they are lost. We've lost the abstraction. And that's only the beginning of the story. As I was saying, this is a very simple workflow. Even in a real world situation, you won't do a single evaluation. You will perhaps want to do more than one evaluation and compare them. See how the number of steps is growing. Here, the Python code for implementing this workflow is not going to fit in one page. Or say another standard workflow, a cross validation, where I split my input data set not in one but in several parts and evaluate them separately and then average over all the parts. How do I solve that? I mean, the kind of problems that I've already seen in very simple workflows are going to grow exponentially as I grow the complexity of the workflow. And one thing that we were well aware of this problem, of course, and one thing that we thought is at first to solve or to make this easier on the client side was to reason, okay, it's easier to explain to the machine what you want to do as opposed to how you want to do that. And by that I mean sometimes you say that by saying that it's easier to be declarative rather than giving instructions. So you want to declare what to do. You want to ask the machine what instead of how. And then since many of these or several or there are a good number of workflows that share the same structure, for instance, a cross validation is always the same. You change the data, you change some parameters, is always the same. For instance, even simpler, for instance, creating an ensemble from an input data set, the specific steps that you follow from the source to the ensemble are always the same. What changes are the inputs, and then you get different outputs. And what changes is the parameters that you use to define your ensemble, but not the process in itself. So why don't we create a tool that encapsulates those templates, those common workflows, and then you specify what you want to do and not how to do that. That's what BigML, our command line interface tool, does. It has inside a series of templates for doing common machine learning tasks. It's implemented generic patterns, generic workflows, and then you can fill in a declarative way the details to ask BigML to solve the problem for you. See, when you invoke BigML here and to create an ensemble, you are not saying anything about the concrete steps that BigML has to follow. You are not specifying the workflow in any way. You are telling or letting BigML decide how all these steps can be performed by themselves. You just declare the parameters of your ensemble. You say that you want 500 models, that the sampling rate has to be 80%, that your input is iris CSV, but that's it. You don't say anything about the workflow. You can apply that to many other ideas. You can apply that also to creating data sets and specifying different input parameters, still declaratively. I'm not telling anywhere the machine what steps to follow. which steps to do. I'm just telling what I want, the end result. And that generalizes also pretty well to things like a cross-validation. A cross-validation is a thing that's defined just by the input data that I want to use and the number of splits, of the initial splits of faults, as they are called, k-faults, that I want to use. So BigML has inside a efficient implementation of this cross-validation workflow, and is happy to do it for us, given only a declarative definition of the problem. I'm telling BigML what I want. I want to analyze this data set, and I want to use cross-validation, and I want to use 3 k-faults. Do your job. So we've gained a bit of back, a bit of abstraction. But yeah, the thing is that this works for this is all good, and it works for some predefined workflows that we know that are useful. But of course, new workflows come up every day, all days. And here, for instance, is another example. It's very typical that we are going to use to combine supervised and unsupervised learning. You already seen examples, and you will do a score, and then you will combine that with some data transformations, and then finally the end result is going to be a classifier, and so on and so forth. And it's very difficult for us to predict or to foresee the exact form of such workflows in practice when we are coding a declarative tool such as BigML, and then things can only get worse. Here's another example of a workflow that the Azure team was proposing to predict channel. So see, all these little boxes are steps in a workflow, and although I think one can do a bit solve this problem a bit easier with model platforms, it's still staggering the number of steps that are there. And of course, it's not possible for a tool like BigML to encompass that, to foresee all those possibilities. Here's another. There are many workflows that you can also, that you don't know how to, or what you would. I mean, if you tell me that, okay, we are going to need that workflow like many times, I could code it in BigML, but it's not going to satisfy all our users' needs, right? So declarative tools help in a way, but are hard to generalize. They are also hard to combine. A nice thing about the bindings and about the APIs is that you can take little pieces together and recombine them and create new solutions. When you have big chunks of code, of templates encoded in this declarative way, that's fine if that's exactly what you want. It starts to get difficult. It makes difficult to combine different solutions and to tweak them and make them working together. And again, we are still talking about client-side solutions that are going to be hard to sandbox, to put once you have a collection of on one side API calls, on the other side bash or shell scripts calling BigML, and you have to make them work together. That's need very serious version control and a very controlled development environment if you want to make that reproducible. So that's a challenge, and we still have, of course, the previous challenges introduced by bindings. So summing up, we are trying to implement workflows on the client side, and we are finding solutions, but we are also finding that the problems that we had solved by going to a server-side solution, by going to our nice JSON-based resources, are back with us. We had managed with our platforms, we had managed with our API to wash away the algorithmic complexity involved in doing machine learning. It was also very nice to have these on-demand elastic services that washed away all the problems regarding computing resources management. I can have as many machines as I wish without having to worry about setting them up, about recovering from errors, about making them parallel. And suddenly all those nice things that I had, all those problems that I didn't have, are back. So what do we do? And well, and what do we do also to scale? Uh, we've seen those problems already back with a simple cross-validation or a simple evaluation. What if you want to go for a real, more complicated workflow? So let's see. This is what we've tried so far. We started with in our server with an HTTP REST API, and we had this abstraction, and we had this automation capabilities, and okay, we wanted more abstraction, and the web UI was good at giving us more abstraction, but it wasn't that good at giving us automation. We had the bindings. The bindings are not as good as the web UI in terms of abstraction, are still better, of course, than just calling the API using HTTP calls. The bindings give you a layer on top of that. You still have to deal with details. Remember that API .ok calls. And then we said, okay, we want more abstraction, more even than that. How we simplify that? And we went for BigML for declarative tools. But we've seen that they are not enough, right? That they are not flexible enough, and we are reaching here this vertex where we have automated things on the one side, we have improved abstraction on the other, and we are finding that that's not enough. So how we solve this problem? Well, let's go back to the server, right? We started here in the server, and we were happy in terms of abstraction. We were happy in terms of automation when as long as all we want is a single resource, we are perfectly happy with automation. We are perfectly happy with abstraction. Can we bring back our workflows there where we were happy instead of going up and right? And of course, the answer is yes. We want to go back, but remember that we also want to avoid. So going back is going bringing my workflow back to the server is going for sure. If I'm executing things there, is going for sure to solve for me scalability problems. I'm dealing with errors. I just ask the server to do it for me, and that's going to work. Is still going to be good for avoiding complexity in terms of having to explain to the machine all the little steps that has to perform and all the little decisions at every step that are needed to make things work. Well, for that, what we need is not only bring the workflow to the server, but express it in an abstract way. And the way we have to do that in programming and in computing science, in computer science, is domain-specific languages. We want to have a language that speaks the language that we are using there that speaks about our domain. Our domain is solving machine learning problems. Our domain is not network errors. Our domain is not parallelization per se. What we want is to say, oh, this workflow is going to create an evaluation. This workflow is combining models, or this workflow is using anomaly detectors. So you want a language that insulates you for all the details, the little details that you are forced to be aware of when you are using a general purpose language such as Python or Node.js or whatever. You want a language that is where the machine learning concepts are first class, are the natural concepts that you use. And for that, what you have is a domain-specific language. This is something that a few months ago I was reading news there that even Facebook has realized is the right thing. They put it saying that artificial intelligence might need or deep learning, because well, you know better by now the differences between deep learning, machine learning, and artificial intelligence. As usual, they put it all together here, but they are conveying the same idea that existing programming languages are most probably too complex, too general to deal with machine learning, and that what you need is a domain-specific language. So that's our solution, and that's what I'm going to tell you more about in the next few slides. We call this domain-specific language that lives in the server with ML. And again, the idea in a nutshell is very simple. It's two parts. Workflows, instead of being things that you implement and you code and you execute on the client side, become resources, become things that live in the server and that you call, that you instantiate and you run in the server. So for you, from the outside, it's just another API call. And it's as insulated, as abstract as creating a model, as creating an optimal, as doing any of those operations that we love. It's just that the operation now, instead of creating a model, is going to be a workflow. And since these workflows cannot be predefined, cannot be a fixed set, has to be flexible, we provide a language, a domain-specific language, to, in as simple a way as possible, specify how those workflows operate, and that's the WSML. And with that, we are going from all our travels on the client side to all those troubles, all those problems hidden away from us and dealt with by the service, which is what you want. You want to forget about problems. You have enough problems in your problem domain. You want to solve your domain specific, your business case, your customers' problems, and not the machine learning problems, and not indeed the problems associated with the workflows that need to be executed. So yeah, the idea is relatively simple. If you want to define a domain-specific language, what you want is to have is a set of libraries, is a set of scripts, and a set of executions of those scripts. So you write your workflow using a domain-specific language that specifies the workflow. You can reuse those workflows, and that's why you have libraries. But other than that, that's the only difference between a script and a library. A script is a full program. A library are bits and pieces that you can reuse among scripts. Nothing very shocking there. And then every time you want to execute your workflow, you have your script that has a set of input parameters. What data set I want to use. What's the number of models in my ensemble. Remember that declarative way of specifying the solution to your problems, that's inherited by these workflows. Then once you have the workflow, which is the pattern and the inputs, you put them together and execute it, and then you have an execution, which again is another resource. Is all these things are things that live in the server and that you can manipulate using REST API calls in the same way that you can do with any other resource. That means that you have almost perfect, seamless interoperability between the two kinds or the two worlds. Actually, there stops to be two worlds, right? We had, before having the workflows in the server, we had on the one hand our resources, models, data sets, evaluations, whatever. We had them, and we also had the workflows or processes that were manipulating those resources. Now we are making that distinction far weaker. We are making also resources all those workflows. And then a workflow can manipulate all kinds of resources, and a workflow can manipulate other workflows, and all gets fused together in a single whole that is going to give us a bit of power. You see. And of course, once you have reified those things, those scripts, you can share them. So you can go to our gallery, and every time you write one of these new templates, one of these workflows, you can put that in a gallery. You can share it with whoever it is. And remember, anyone can use it because it's now a resource that lives in the platform. So any user of the platform, regardless of the language that they use or whatever, can directly use it. They don't even need to look at the implementation or at the details. We are abstracting away all the details. I don't know here, for example, there's a script that performs DIMnet scaffold cross validation. So if I read the description, I understand the inputs, I understand the outputs. I can use it without having to understand the particulars of the algorithm inside. So that's exactly the same kind of abstraction that we had for the resources already there, that we had when we were creating an ensemble or when we are doing a boosting. We can use it without going into the details. We can now use these scripts in the same way, with the big difference that these scripts are extensive. And it's now our customers that can also help and grow the platform as they wish and make it something more useful for them. And that's the thing that I was also talking about before, that since they are the same kind of thing, since they are all resources, the interoperability that you find between them is seamless. They can call each other. They can interact with each other. Let me show you an example of how this is really powerful. This is my account in BigML, and here I have my data sets. Say I have this IRIS data set, right? And say I'm doing this workflow again, no? And the thing that I wanted, I have the data set. Now I'm going to do a training test split, and let's use a seed so that next time I have new data, the seed is the same. Now I'm creating my training and test. Now I know I've learned my lessons, and I know that the training is the one here in the training hub, 120 instances. I know that is here where I have to create a model, and then maybe I have to do some configuration of the model. Here I'm not going to change anything, but in a real case, I will be changing things and deciding what I need and what I don't need. Here, when I'm happy, I will create my model, and of course I know that it's not. This model is not ready yet for production because I have to go first and scriptify the thing. So, and evaluate the thing. So I'm going to evaluate my model. I've already have here pre-selected the test data set that looks good. I create an evaluation, and here I'm now happy. I look at the confusion matrix, and I try to decide whether this goes to production or not. And now I want to repeat this. By now I've forgotten half of the steps that I took before getting here. But since I have this thing that's a workflow, and since I have these things, this language that knows how to deal with resources, this language is going to be able to look at all the steps that I've performed so far and generate for me an automated script, an automated workflow that will repeat the thing. That's what Scriptify does. I can go here and scriptify the evaluation. Then in our servers, what we are doing is recovering this evaluation, is looking what's its parent. This came from a model and from the data set, and from a data set. The model was created from another data set that was half of the split that was used for creating the evaluation, and in the end, that initial data set came from a source that was read from a remote URL. And since all that history is recorded in the server, As an aside, that's also thanks to the fact that all our resources are immutable, which is a very important property. So I can recover the past. Since all this past is codified in our resources, I can automatically generate a script. I can automatically generate one of these new resources called WisML scripts that will repeat all the steps for me. And one nice thing, or one thing that I find amusing about this is that all this process that I've just described, this thing about looking at the resources that you have, looking at its parents, and so on and so forth, is a process that is looking at our resources. Is a process that can be performed by WisML itself. So the program that's generating this WisML script that repeats the process for me is itself a WisML process, which ties it up all together very nicely. And here you see how this is a resource. You see this is the source code that was automatically generated. This is the DSL inside. You see the inputs. These are the declarative aspect of the whole framework, where all you need to know to perform again this workflow is what are their inputs, is what you are going to do, is not how you are doing that. How you are doing that is codified here in an abstract way that you don't even need to look at this stage. And of course, when you execute, you will have outputs, and then you have also a nice way of putting together the resources. That means that when you have executions, they will have outputs, and since they are resources, you will have all the outputs of the execution packed in a single resource that then you can use in other scripts. And maybe you can pick inside the results of a previous execution and take decisions using those results. And for that, it is paramount. This is very important that these executions are also resources, because all WisML knows how to do is dealing with resources, and it does it well. So this is good, and let me try to here. I'm back to the presentation. So this is another of the advantages. And now let me show you a bit how this DSL works syntactically. Remember, this was how I wrote the initial simple version of my script to create an evaluation, a split and an evaluation, and how it was already a bit complicated, and how it wasn't half of the story. If I wanted to do this really scalable and really production ready, this wouldn't do. But even here, if I want to repeat that, what I'm doing here using WisML, this is how it looks. Now forget a bit about the concrete syntax and just try to read it. You are just using verbs that have to do only with machine learning. I'm creating a dataset split, I'm creating a model, and I'm evaluating. There's no way here, there's nowhere here where I'm waiting for things, where I'm dealing with errors, where I'm doing anything. I'm only talking about the parameters of my problem, about the things that I want, the machine learning entities that I want to create. That's how it is abstract, and that's how, of course, you see it's much shorter already than even the simplest Python script that I can write. And what's worse, better, what's best is that this code, as you see, it is already ready for production. It's going to run in the server. It's going to run smoothly. If things fail, retries are going to be in place for me, and all I have to do is wait until it finishes. And what about making it work for 100 datasets instead of one? Remember, I showed you lots of Python code before very quickly, but just to give you an idea, in WisML, since this is an abstract, this is an abstract language, since this is a domain-specific language, to go from one dataset to 100, I just go from this code to this code. Sorry, from this code, this is the one for one resource, to this code. Let me do that again. This is for one resource. I'm creating a single evaluation here from a single dataset. I'm doing this for any number of input datasets. So you see what I'm doing is just instead of having one instance of each, I just do a for, which is create a list of splits, and then I do another for with each split, just create an evaluation. So you see the complexity just is like 2 or 3 orders of magnitude less than before, because moreover, this is already ready for production. This is going to run in the server. This is going to be parallelized. I don't have to make any decisions about how to run these data sets or these evaluations or these models in parallel. This is going to be done for me at the server level, where moreover the system knows how many parallel tasks you can run. So it will auto-scale to your level of parallelism for you. It will also know where to stop or how to recover from errors and do that for you. And again, all you have to do is wait, this time a little longer, because maybe I have 1,000 data sets instead of one, but you just wait. And this will be an execution running there, an evolving execution, where you will get notifications as often as you want with updates of how it goes, how many resources it's created in the way, and on the way, and so on and so forth. So I've gone from pages and pages of client-side scripting to just 3 or 4 lines of domain-specific writing, if you want, if you will. And also note also that this is the same for all customers. You can modify that, and that solves the problem, no matter what language you want to use on your side, because you can still have scripts on your side. Then maybe you want to have a script that runs 3 workflows, and for whatever reason you prefer to have that as a script on your side. Even when you do that, your scripts are going to be simpler. Here is that same example. If I've already created this script that does the workflow for me, calling it from Python is just 3 lines. I just create an execution and just wait once for it. I give it I use the inputs. That's the data set that I want to use. That's the script that I want to run, and I just execute it. And that's again ready for production. My client-side code doesn't need to be more complicated than that. And if I want to go from 1 to 100 data sets, my code is like that. It's not getting significantly any more complex. It's just substituting a single data set for a list of data sets. And I'm done. And this is production ready. And I can call the same script that I wrote once and put in the gallery. You can call it also from your client side in Node.js or in C++ or in Java or in COBOL. And so we have interoperability still with us. And there are many things. That's not all. So any workflow that you want to, or almost any workflow that you want to create, you can create. You can also go to the gallery and reuse workflows from other people, but that's not the end of it, because moreover, it's clear that this can be useful for short tasks, like I have to do this thing over and over again 100 times, and then I want to do it in an efficient way, and I don't want to repeat myself. But know what? There's more that you can do with these workflows, because as it happens, many of the machine learning algorithms or machine learning meta algorithms that you use in a day-to-day basis are little else than short tasks, little else than a loop where you go, you create a bunch of resources and evaluations, you look into them, you compute a summary of the results, and then you say, okay, is this good enough? No, it's not good enough. Next loop, and you repeat that again and again and again until you converge or you get bored. So that's perfect for this kind of algorithm, for this kind of, not of algorithm, for this kind of language, for this system, for this way of performing workflows there. So it turns out that we can extend even the machine learning, the intensively machine learning parts of the platform by ourselves using workflows. For instance, this is a very quick example just to give you an idea of the kind of things that you could do. You could go and do this and think, why don't I perform, instead of using just a single model for making predictions, why don't I use a collection of models? That's the idea of an ensemble, right? But what in an ensemble of the models are of the same kind. What if I wanted to generalize that and use to make it predictions to predict things, to model my data? You see here 2 columns and a numeric columns and a categorical field. I want to predict the categorical field, and instead of choosing between a tree, an ensemble, and a linear regression, why don't I use the 3 of them? So there's a strategy for that called stack generalization. It's a very well-known methodology in machine learning, and in there what you do is, okay, I take half of the data and I create the 3 different kinds of models that I want to use, and then I predict using each of these models, using another half of the data. So I use half of the data for creating my models that are going to predict this column here, A, B, C, D, and then once I have my models, I predict actually with each one the values of this column. And then I have 2 things. I have the real world, what I had for real, the supervised labels, and what my models predicted. So I have a data set that tells me what's the actual solution when my first model predicted A and my second model predicted B and my third model predicted A. The solution, the real solution was A, and so on and so forth. So what I have here is a data set that has as inputs the predictions of my models and as output the real model. So I can create a model that models that. And what I will do later on is, okay, when I get new data and I have to make a predictions, I will use my 3 models. I will create the 3 columns of predictions, and then I will use my meta model to get the actual solution. So each model is predicting something, and I combine their predictions within another model to get the real prediction. So this is a common thing to do in machine learning, and we don't have it implemented in BigML in the platform. But what if I want to do that? Turns out that things like that are easy to code in WisML. I can go from here, from this idea, I want to create 3 models. I want to take half of the data set and create 3 models. This is very easy to say. I want a random data set split into halves. See here, and now I want to create, this star means create more than 1 model. I want to create a model, an ensemble, and a logistic regression. These are the parameters. There, I've created this thing. This part of the workflow is this handful of lines in WisML. The next thing I want to do is to use each model to predict over the rows of the other half of the data set. And that can be done, again, I won't go into details, but just to give you an idea of how simple writing these operations can be in a language like WisML. It's again like 5 lines. I can create this data set here that puts together all the predictions and the real one with just these few lines of code. And then once I have the data set, what I have to do, this new data set, what I have to do is creating a model. I can do that. And it's even simpler, right? I already have I have the data set, I just have to create a model, and I only have to be careful that I exclude the inputs that I don't want, the original ones. And then I'm done. All said and done is this non-trivial machine learning algorithm is implemented in a page, almost. Yes, it fits in a page of WisML. And then it can be reused by anyone. And then, of course, when I want to predict, I have to go to the making the predictions, but they are, again, very simple operations to do in WisML. So yeah, so with all this, so we have many bases covered here, right? We have automation, we have scalability, we have abstraction, and we are even able to do real machine learning, not only maintenance, not only chores, but also real machine learning algorithms using our system. And we bring together all the goodnesses of abstraction, of that are provided by a REST interface, and we brought into that nice world all the complexities of the world of workflows. So we are probably, are we there yet? Are we happy with what we have so far? Just a last word on this. We are never happy, right? But in machine learning, the ideal state probably would be just, let the machine do everything for me. Let it be really intelligent. I just give you my data and tell you, do the best you can and give me a result, predict whatever it is, and don't bother me with the details. You'll see that we've been working towards that. We have things like OptiML, like AutoML, automatic model selection. It's machine learning. It's the machine working for me, analyzing my data, creating thousands of models for me, exploring the parameter space to tell me what's the best model. I don't even need now to go and think about which algorithm should I use. It's not only that the algorithm, I don't need to know the details about the algorithm. It's that I don't even know to choose which one to use. We've been seeing in this presentation how DSLs are helping us. We have other DSLs in the platform. You have also seen Flatline, which is a DSL to specify in an abstract way data transformations. You can call Flatline from WSML, our other DSL, and we see how these DSLs allow us to specify problems in a more declarative way. Again, like this monkey here ones, like I say what I want and let the machine figure out how to do it. There are parts in our DSLs, that's why I say we are working on it. There are parts that could be more declarative. I still have to specify some steps. Not all of them. There are a good deal of steps that I can gloss over, but there are still steps that I have to specify when I write my WSML script. So the challenge there is to make it even more declarative, and we are working on that. And finally, to just get to that perfect world, what we will need is automatic feature engineering, and that's still a bit of black magic, and that's still 80% of the time that you spend in your machine learning project, because since all the other tasks are so streamlined, since you have at your disposal such powerful tools to perform the machine learning part of the job, the modeling part of the job, now also the workflowing part of the job, what's left for you is to get the good data, because your models are to be only as good as your data. So there, we still have ways to go until we really let the machines do that for us. And with that, I'll leave the mix to you and accept questions. Thank you.